Today's webinar will be presented by Justin Heavey, who's worked with environmental sustainability projects in higher education since 2008, with a focus on shrub willow since 2011. He currently provides a range of technical, analytical, and educational extension services to advance the expanding willow industry in northern New York State. He holds a BS in Environmental Studies and an MS in Natural Resources Management from SUNY ESF. His work with SUNY and the New Bio project now brings him to speak with us today about the economic model EcoWillow 2.0, which is an updated version of a model that has reached over 1,000 people around the world. He'll be telling us a bit about those updates and taking us through some examples of how the model works. Justin is joined by Tim Volk in his office, who won't be speaking in this presentation, but who will be available to answer questions at the end of the presentation. Tim is a frequent speaker in our webinar series and brings over 25 years experience in forestry, agroforestry, short rotation woody crops, bioenergy, and phytoremediation, and whose current research focuses on shrub willow in particular. So for this program, Justin is sharing his screen with us live today rather than showing a presentation file. So we recommend watching this webinar in full screen mode to help you see the details on the spreadsheet. Justin, go ahead whenever you're ready.
Okay, thanks very much, Sarah, and thank you to the New Bio project for hosting today. This is Justin, and like Sarah said, Tim is here with me, and I'm going to go through the presentation, and then we'll both be available at the end to answer questions. So this is EcoWillow 2.2. Basically, this is a model for the financial analysis of shrub willow crops. So a quick overview of what we'll cover in today's webinar. We'll give a little bit of background in the history of development of this tool over the years. List and explain some of the updates that we've made in this recent version, which is version 2.0. We'll give a brief tutorial of the model itself, as well as some of the newer features. We'll run through 4 example production scenarios of crop production and look at the outputs of those scenarios and how different variables affect the output of the financial analysis metrics. And then we'll also leave some time at the end for questions and discussion. So a little bit of history on EcoWillow. This was first released in 2008 as EcoWillow 1.0. It was created and released by Thomas Buchholz and Tim Volk here at SUNY ESF. From 2009 to 2012, minor updates were made to the model and released as various versions of 1.0. Again, over that time, it was pretty widely used, not just in the Northeast or North America, but all around the world. Over that time, there was also a few journal articles published on this tool and the different aspects of it and incentive programs and the effect on prices and things like that in the Journal of Bioenergy Research. So that's kind of the previous history. Then more recently, in 2013, we began making comprehensive updates to version 1.7 by myself, Ayushi Patel, Mark Eisenbies, and Tim Volk here at SUNY ESF. And we were also assisted by Cato Analytics, the Celtic Energy Farm, who are willow growers here in New York State, other stakeholders from the regional industry, as well as New Bio partners. So all that effort culminated in October of 2014 when we officially released EcoWillow 2.0. And if you haven't downloaded it yet, it's available at our website. If you go to esf.edu/willow and then just follow the links to EcoWillow from there. So that's some of the background on the model. More specifically, in the newer version, some of the things that we've tried to incorporate are mainly data that we've collected from commercial scale production in New York State. Things like harvesting and planting rates collected through the use of GIS technology, the current price that's being paid for biomass and other market considerations, current costs of materials and custom rates for doing some of these farming operations. We've also included recent research on biomass yield, moisture content, and things like that, as well as a project that's been ongoing for several years in partnership with ESF and Case New Holland to develop a woody crops cutting header that fits on their forage harvesting systems. Additionally, we've had producer and stakeholder feedback, people who have used the model, who are actually growing willow, and we've tried to incorporate their suggestions as much as possible to make it as user-friendly for people who are actually using this model. So some of the things Under that category include things like including inputs and outputs on a green weight basis. Previously, it had been just a dry weight basis, which is not exactly practical. People who are actually producing willow in the field are, they're cutting wet tons, they're transporting wet tons, and it's wet when it gets to the end use facility. So we've changed the primary way that things are input and output into green weight. Wet weight or dry weight is still available, and I'll show you that in the model itself. We've also included things like the ability to put multiple field locations into one project analysis. Previously, you could only look at one field at a time. This model allows you to look at multiple fields, and again, I'll explain more of that when we actually look at the model. Also, we've had minor things like bug fixes and tried to make it a more user-friendly design. We've created a slew of supporting documentation, so we have 3 fact sheets, and also there's information within the model itself, such as a tutorial. And then we've also created some example production scenarios using this model that we'll also talk about. So that's the background and history of development of the tool and some of the updates to version 2.0. I'm going to switch over now to the actual Excel model and go through a brief tutorial and some of these example production scenarios. Okay, so this is what you see when you first open the EcoWillow model after downloading it from our website. So this is basically just an Excel spreadsheet. Today for this presentation, we're using English units, but there is both an English units and a metric units version available on our website. So whichever is more comfortable for you, you can use either one of those when you run your own scenarios. So when you first open the model, this is what you see. This is basically just a welcome screen that provides basic info about the model and its functions. The model has different modules and graphical outputs, which are controlled by different tabs, which you can select on the bottom of the screen. So there's actually 5 input modules, a fields module, an input-output module, which is the main module of the tool, the planting submodule, the harvesting submodule, transport submodule, and then there's 4 graphical outputs. So cost distribution, a graph for yearly costs or yearly cash flow, accumulated cash flow, and then the itemized cash flow. And then there's also a tutorial on the last tab of the model that explains each one of these modules in more detail. So going back to the input-output module just for a second, I'll explain the basic parameters of this model and how they're input. So if you look at any of these modules, you have basically 2 columns, and on the left are your inputs and subtotals, and then on the right column, you have meta outputs for the model and each submodule. If you look at each one of these lines, each one of these basically represents one variable in the Willow production system. So if you read it from left to right, what you have is basically a description or a name of the variable. Going to the right, you have the unit that variable is measured. The yellow boxes are input cells where you input what that variable is in whatever scenario you're modeling. And then to the right of that, you have a suggested value, and I'll talk more about those. But the suggested value also corresponds to the default value. So like I said, the yellow cells are input cells, and then you have subtotals in these gray cells, which can't be modified other than changing the input cells. And basically your inputs are put on this left-hand column, and then your outputs appear on the right-hand side. So also for today, you might notice that some of these categories are highlighted in blue. You won't see that if you actually download the model from our website, but I just put that in there today to direct your attention to key variables as I talk through them and go through different scenarios. So now I'm going to explain a little bit more about each one of these modules individually. So starting with the fields module, like I said, this is a new feature in EcoWillow that actually lets you enter data for up to 20 individual fields. So this list goes all the way down from 1 to 20. So each one of these represents either a different location or multiple fields at one location, which might have different characteristics. There's also a feature in this submodule that's a calculator that allows more precise calculations of headlands and unplanted area. So for different fields, you can enter the field length and width and other aspects of headland depth, sides of that you have headlands and things like this, as well as additional acreage that might be left unplanted. And what this does is allow more precise estimates of your actual planted area based on your field size, geometry, and other areas that you might leave unplanted for hedgerows or landing areas and things like that. So for this mod, this calculator just calculates fields individually. So you would calculate your field area from here and then input it individually for each field on the left. So for example, here field 1, just named field A. The field area in acres is 25 acres. Then you would enter your percentage of headlands and unplanted area. In this case, it's 20%. From there, the model calculates your acreage that's planted and unplanted. And then you also enter your transport distance for each field as well. So from there, the model will take each one of these fields and total them all up. And the outputs from that will appear on the right side of the screen here in your total field area, total planted area, and also your average transport distance, which is weighted by the amount of acreage in each location. And also, I forgot to mention earlier that if you see a red tab near any one of these cells, really you just need to hover your mouse over this, and that will show you more information or instructions for that cell. So this one is indicating that when you enter the transport distance, that's actually the one-way distance that you're hauling to an end user. So again, the inputs from the left here are summarized on the right, and then from there, they're fed throughout into the input-output module and the other submodules throughout the entire model. So that's a quick summary of the fields module. We'll go next to the input-output module. And like I mentioned earlier, this is basically the main module of the entire EcoWillow. So here you want to have your general data inputs first and foremost. So things like your biomass yield that you're expected, your annual increment of that. Again, here this is measured on a wet basis or green weight, so tons per acres per year, biomass yield, wet basis. Also things like your price paid for biomass or what you're expecting to get paid at your end user. And your interest rate and other general things fall under that category. Beyond general data, you also have separate sections for where you can input possible incentive programs and the details of whatever those may be, your input for crop establishment and maintenance. And then also on this page, you see appearing subtotals from some of the submodules, so planting costs, harvest cost, and transport cost. Again, these are subtotals that are coming in from these other submodules. So those are your main inputs and your summaries from other submodules. The outputs from all that and from the entire model appear on the right-hand column of this page. So basically, you have some pretty standard financial analysis metrics. So net present value, internal rate of return, and then the other one that I'll draw your attention to under the production costs and revenues is the break-even price. And this is basically your production cost per wet ton, including incentives that might be factoring into that. Under net present value and internal rate of return, you also have some standard adjustments of optimistic or pessimistic scenarios or adjustments. So what these are is basically, so for the optimistic, it's simply plus 10% in revenues and minus 10% in expenditures across the board. And then the pessimistic is the inverse of that. And then we also have this broken down into 13 and 22-year outputs. So today, and in general, we focus mainly on the 22-year life cycle, and that assumes basically the full life cycle or the expected life cycle of a willow planting. So 22 total years, which is about 7 rotations on a 3-year harvest cycle. Also, like I mentioned earlier, the model now primarily runs on wet weight and inputs and outputs. But we also have some dry outputs down here, so you can see the production cost at 0% moisture content, as well as the harvesting and transport cost also in dry weight. So that's kind of the overview of the main input-output module. Next, I'm going to click on the Plant tab and go to the Planting submodule. So this one is fairly straightforward. General information, the big variable here is your planting rate. The total area to be planted comes from the Fields module. And then whatever planting rate you have, it's calculates your total planting time. From your planting time, that number filters down through these variables of labor and equipment, as well as supplies. And that calculates your total planting costs, which are summarized over here on the right side. Again, your total cost for labor, travel, supplies, your total planting costs, and then your planting cost per acre or hectares if you're using the metric version. That's the planting submodule. Next, we'll go to the harvesting submodule. So this module has had a little bit more comprehensive updates to it in this version of EcoWillow compared to previous versions. And a lot of that has been based on the development of a specialized short rotation woody crops cutting header that's been developed by SUNY ESF in partnership with Case New Holland over the past 5 years or so that fits on their 9000 and FR series of forage harvesters. So in this module, if we start just up at the top under the general heading here, the key variables here are standing biomass at harvest in units of tons per acre, the field capacity of the harvesting platform in acres per hour, the material capacity or the speed of the harvester in tons per hour, and then related variables of the row length, the downtime of the harvester, and below that, efficiency of collection vehicles, etc. So here, your tons per acre standing biomass is based on the user inputs of rotation length and average annual harvest. So in this case, we have 10 tons per acre assumed biomass production every year and a 3-year rotation. So when it comes time to harvest, you have 30 tons per acre standing biomass. The acres per hour harvest rate is calculated based on the expected performance of this harvesting platform at that level of standing biomass, which is entered by the user. So this variable, we've made a suggested value, which is automatically input into the input cell here, but we left it so this variable can be adjusted based on expectations of efficiency and other variables that you might have, such as your ground conditions or your operator skill and things like that. So basically, these variables that we've determined the relationships between these key variables of harvester system performance and the amount of standing biomass are combined with these other variables of row length, how long it takes the harvester to get down the field, how much time is spent turning around and backing up into headlands, the percentage of harvester downtime also factored in there. So these come together and basically create a harvest time that's an estimate of how much time it's actually going to take you to harvest the amount of standing biomass you have based on your field conditions and your other assumptions. So these costs are then filtered down through based on the total harvest time and your variables that you input of equipment and labor and all these things. And I should mention that it's important to remember that we have suggested values for each of these, but it's really dependent upon the user of the model to whatever production scenario or whatever situation they're trying to model to actually go through each one of these and verify that whatever the variable, the suggested value that's input in here by default matches up with your situation. So it's finely tuned to what you're actually doing on the ground or what you think your production scenario is going to look like. So those are the major changes and the inputs of the harvest module. Again, costs totals appear on the right, total labor, equipment, and also totals breakdowns based on your dollars per acre and your total per wet ton. So that's an overview of the harvest module. Transport module. Again, this is fairly self-explanatory, fairly straightforward. Basically, this is just to calculate your cost to an end user. The amount of biomass you're transporting is calculated previously in the model, so it comes out as a gray output or subtotal cell here. You can change variables like your truck speed, your loading time, dumping time, and things like that. All that, again, calculates your total time, your total cost. You can have the option to use a loader or a blower to transfer it from short-term storage into your transport vehicles. And then your outputs, as always, are on the right side of the screen, your total transport cost, and your cost per acre and cost per ton. So those are the input modules, and we'll look quickly just at some of these blue tabs, which are the graphical outputs. So this is the cost distribution. Basically, this is just the summary table on the right and a bar graph on the left that is broken up into what we see as the main categories of costs across the entire production system. So in this scenario, land costs are about 14%, small percentage to administration. Establishment is a high one-time cost, so it can be up to $1,000 per acre or possibly even a little more than that. So it only happens once, but it's expensive, so that makes up about 20% of your total costs. Fertilizers in this scenario are a very large percentage of total cost. It happens at every harvest with this scenario, so about 8% of your total costs. Harvesting is going to be a big cost because this happens multiple times across the 21-year life cycle of the planting. Transport, again, with that 25-mile one-way transport distance, your costs are about 20%. And your stock removal, which indicates what it costs to remove the planting, so we include that cost of what it costs to tear out the willow actually at the end of the 22-year cycle. That's about 7% in this scenario. So these individual numbers probably will shift slightly depending on your individual scenario, but this is a good rough estimate, plus or minus, say, 5%. This is, generally what, ballpark of what your cost breakdowns are going to be. So that's a cost distribution tab. We look at the next graphical output. This is a yearly cash flow graph, both on a per acre and a total project basis. So this just tells you basically if you're in the red or black in each individual year and how much. Going next to the accumulated cash flow tab. This is a little bit more informative, I would say. This shows the undiscounted accumulated cash flow, again, on a per acre. I have it zoomed into per acre, but it also shows total down below. And it also shows lines for the, your expected or realistic scenario or adjustment. And then, like I mentioned earlier, those optimistic and pessimistic adjustments. And basically, wherever this line crosses the 0 point, that's your break-even point. So that's a useful metric in addition to the ones on the main input-output page. And we'll come back to this later as we go through some of the production scenarios. And then the last output is just the itemized cash flow if you want to really look at where things are occurring, where costs are occurring in specific years. And this also is on a per acre or per hectare and a total project cost basis. So that is kind of the quick overview of the entire model. From here, what I'm going to do is demonstrate 4 crop production scenarios that we developed as we developed EcoWillow 2.0. So it's important to point out that these are really just hypothetical situations that are designed to show the impacts of some of the key variables on the economics of production for willow. And again, users are definitely expected to change all variables in this model to match their specific production situation or whatever scenario they're trying to model. So like I said, we have 4 scenarios to present today. Number 1 is a conservative base case scenario, and this is actually what is pre-entered into the model when you first download it based on all those suggested values 2014. The second scenario is an incentivized scenario, and what this does is add possible BCAP or Biomass Crop Assistance Program incentives to the base case. The third scenario is what we call an improved scenario that adds suggested best practices to the base case. And then the fourth scenario is an improved/incentivized scenario that adds both incentives and best practices to the base case. So the first one we'll look at is just the base case scenario. Like I mentioned, this is a fairly conservative estimate of profitability based on the, some of the data that we've collected over the last several years. and this is pre-entered when you first download the model. This is the base case scenario. So some of the key inputs for this scenario include the minimum recommended project size of 25 acres, a 22-year life cycle of the project and the planting, a planting rate of 2.5 acres per hour, 5,500 stems per acre planting density at 12 cents per cutting, a 3-year harvest rotation, and a biomass price paid at the plant gate for of $27.50 per wet ton of biomass, which is close to the current rate of what's being paid in New York State, where some commercial willow production is now happening. So like I said, everything is already pre-entered for the scenario when you first download it. If we look at some of the outputs on the right side of the screen for this module, or for the scenario, they're not particularly favorable. The NPV and the internal rate of return under the expected adjustment is negative. The break-even price is just under $30 per ton, so that's actually not too high, but it is still higher than the price that you're expecting to get for the biomass, so you're actually losing a little bit of money on every ton delivered. But if we look at the optimistic adjustment here for internal rate of return, so plus 10% in revenue and minus 10% in expenditure, you can see that the internal rate of return is actually positive here. So that tells you you're not really too far away from a situation that has positive economic returns. So that is the quick overview of the base case scenario, the inputs and the outputs. Next, I'll talk a little bit about the incentivized scenario. So one of the main catalysts here in New York State in the last few years of actually getting willow acreage installed in the ground and purchased by a dedicated end user has been the USDA Biomass Crop Assistance Program. And this program in 2013 was actually responsible for either planting or otherwise enrolling about 1,200 acres of willow crops in northern New York State into this program and getting them established with a dedicated end user and Bioenergy, who's a biopower company. So the possibility for future incentives such as this or other similar programs do exist. So to evaluate the possible impact of this or similar programs on the conservative base case scenario, we can enter the expected values for this program in incentive section of the input-output module. So that's right under your general data here. So one of the main things of this program is that it's an 11-year program that contracts an end user with the producers for an 11-year period. But also during that 11-year period, the growers or the producers receive annual acreage incentive payments, which are equivalent to NRCS soil conservation rates. So what we've seen, the average of these are somewhere around $40 per acre. So that's our suggested value for that. So here where it's 0, we're just going to enter that to $40 per acre per year. This is paid in non-harvest years. So in harvest years, it's 0% of this payment. So we leave that as it is. Another possibility would be biomass co-payments for every ton of biomass delivered. We don't expect that in any future funding, but it is a possibility. So we leave that there, but we leave it at 0 for now. And then the other thing that we expect and that we've seen in the past with this BCAP program is establishment grants for every acre put in the ground. So this is a one-time incentive that goes to growers or producers that covers some of the high establishment costs to help them actually get this crop in the ground. So this can be anywhere probably from 50 to 75% of your establishment costs. Again, for willow, the establishment costs are somewhere $1,000, around $1,000 per acre. So figure somewhere between $500 and $750 per acre. Again, one-time payment. So we use here the suggested value, a somewhat conservative estimate of $500 per acre. So we changed just those two variables under the incentive program heading. And if we go back over to the outputs, we can see that the expected net present value under this incentivized scenario is now positive. The internal rate of return is over 5%. And if you look at the break-even price, which again is just the production cost with incentives also factored in there, it's now below $25 per ton, per wet ton. So you can see already just with these two incentives that it actually offers some good potential for profitability of willow. So basically, those two changes make up, the entire this incentivized scenario. So we just wanted to show you that really quickly, and we're going to do the improved scenario. So the third scenario is going to be next. So to go back to that scenario, I'm just going to remove the incentives that I just put in there. So the acreage incentive payment goes back down to 0. And the establishment grant also goes back down to 0. So we're now back at the base case scenario. Returns are not particularly favorable. So now we'll look at this third scenario, which is the improved scenario. And really the concept of this scenario is just to make small adjustments to a limited number of key variables across the production system. And these adjustments are based on what we consider to be realistic best practice targets. So things that we think are achievable and actually should be incorporated into commercial willow operations at this stage of development of the production system. And also expected system improvements that we see as realistic in the near future based on ongoing research and the current market conditions. So the first things we'll change in this incentivized scenario, we'll go over to the Fields tab. And one of the first practices that we recommend, and one of the first things we'll change here, is to actually increase the field area from 25 acres, which is pretty much the absolute minimum recommended project size for growing commercial willow. And we'll actually increase that up to 100 acres. So it's a 4-fold increase, but when you think about commercial production and producing crops on a large scale and economies of scale, you really should probably consider doing at least 100 acres at a time. And what this does is reduce the cost of harvesting by creating longer rows in individual fields and less turn time and less time backing up if you have to in the headlands. And it also reduces the fixed cost per acre of transporting harvest equipment to a site. So if you're paying a certain amount of money to get equipment, harvesting equipment and other equipment to a site, if you can spread that cost out over a larger number of acreage, it lowers your total cost per acre and your total harvesting cost or planting cost per acre. So with that up to now 100-acre field size or project size, the second thing that we recommend as a best practice target is maximizing your planting area relative to your headlands or your unplanted area. So what this does is maximize the land area that you're actually growing willow on, and minimizes the area that's not in production, while at the same time also maintaining adequate headlands, which should be at least 30 feet on 2 sides of the field on the ends of the willow rows for the ability to smoothly turn all of your machinery and not have problems there. So related to this issue of how much percentage should be dedicated to headlands and other unplanted areas, and what's the reality in commercial fields when you plant larger scale acreage. This past summer, we had a new bio undergraduate student scholar, Isaac Niffing, spend a lot of time looking at commercial fields and actually going out to fields and recording using GPS the planted area as compared to other areas and the total tillable acreage in the field. And what Isaac found out was that headlands and unplanted areas range from less than 10% up to 25% of the total field area in the current commercial acreage that is out there in the landscape. So these other areas, you have to leave some percentage for headlands. So, that can be anywhere, 5 to 8 or 10%. The previous estimate in EcoWillow was 8%. But we found that the reality in commercial fields is that, sometimes there's access roads or hedgerows or, areas that you want to keep clean for landing or saturated areas. And these areas actually add up. So we recommend for a best practice target that you keep your headlands and unplanted areas down to around 10% if possible. So I'll change this variable from 20 down to 10%. And this can be done through a lot of ways. So planting design, just being aware of these issues when you lay out your field design and when you actually go out and plant. The other thing is large rectangular fields and long rows reduce the percentage of headlands. And that's another area where this headlands calculator can help you out if you know the length of specific fields and how long your rows are and how many sides of the field you actually put your headlands on. All of these factors add up, and hopefully you can keep that number down to a 10%. So that's another best target practice that we're setting for this improved scenario. Last one on the fields tab is just the transport distance. Transporting, as I showed before, and the cost distribution is a large percentage, even with relatively short transport distances. And whenever you're choosing a location for biomass production or willow production, you always want to keep your transport distances as short as possible to reduce that as much as possible and really locate your fields as close to a dedicated end user as you possibly can. So for this situation, we just assume a modest reduction in this from 25 down to 20 miles one way transport distance. And those are basically the changes that we make to this field inventory module. So if we look quickly at the input-output module, returns are creeping up a little bit, but not too much yet. So from there, we'll go on to the planting module and make some more adjustments for this improved scenario. So like I mentioned before, the planting rate, or the acres per hour that are actually put in the ground during the planting process, is one of the variables that, again, we have a suggested value based on monitoring that we've done, but you can change that variable based on what you think is going to happen in your operation or what you've seen in your operation before. So another new student bioenergy scholar, Charles Bush, again in the summer of 2013, when a lot of this BCAP acreage was going in the ground, took the time to use, again, GPS technology to monitor planting operations up north in northern New York State. And what he saw from that study and the analysis afterwards was this average rate of 2.5 acres per hour. So that's the default use that we use here, the suggested value. But if we look at closer at that data, we actually saw rates consistently around 4 acres per hour and up to as high as 5 acres per hour. So for this improved scenario, again, we just make a pretty moderate assumption, and we assume that our planting rate is actually going to be 3 acres per hour. So that's one adjustment on the planting part of this system. The second thing that we adjust here in this scenario is the cost of planting stock, or the cost per each individual willow cutting that's going in the ground to grow your willow planting. So this is one of the largest costs in the planting process, and planting, again, is one of the largest costs in the overall system. And the cost of cuttings, even though it seems like a small number, 12 cents per cutting, actually has a very large impact on the overall planting costs and systems costs, because you're planting this at 5,500 stems per acre multiplied by hundreds or even thousands of acres. These costs add up very, very quickly. So based on what we know of the production of these cuttings and where we hope to see the market go and where we think it will go as acreage that's going in the ground increases, that's going to create a more steady demand for cuttings that will help lower the cost of this. And we expect to see this price stabilize around actually 9 cents per cutting. So lowering that down from 12 to 9. And again, at 5,500 stems per acre, this actually quickly shaves $100 or $200 off your total cost per planted acre. So making that one adjustment, hopefully the markets for cuttings, the demand increases and the price can stabilize a little bit lower than what it is right now. And again, larger orders will also affect that as well. So again, just 2 little adjustments there, and we've reduced our planting costs. We go back from there to the input-output module, change a few variables here. So if we look at the average annual biomass yield, this is always something that we're trying to improve and hoping will improve. So in this scenario, we're going to increase that from 10 wet tons per acre per year with a moderate adjustment up to just 10.5 tons per acre per year. And again, this is a moderate assumption. We hope we can see this and even more in the near future as a result of stuff we're doing, and then also breeding programs at Cornell University and other areas where one of their main focus is to increase the yield through breeding programs. So we increase that variable slightly, and then the next thing that we're going to change here is just the price of biomass paid at the plant gate. $27.50 per ton is basically what's being paid now. We hope to see that increase at least just a little bit, in the near future. So we're going to just increase that by 50 cents per wet ton up to $28 per wet ton. From there, we'll scroll down a little bit and get into the crop maintenance section of this module. So like I showed you in the cost distribution tab earlier, fertilizers can take up a very large percentage of your total system costs. Part of the reason for that is, fertilizers are expensive, and this way this model works is that it calculates the cost recurring at every harvest, assuming that every time you harvest biomass, you're taking some amount of nutrients off the field, so you want to replenish those. But this is also an area that we see a lot of opportunity for improvement. Again, it's a very large financial cost, but it's also a very large cost of greenhouse gas emissions and energy input into the system. So anything that we can do to reduce this, we want to try to do that as a best practice target. So in this scenario, we have the cost at $65 per acre for fertilization, again, recurs at every harvest. So our best practice target here is maybe a little bit more aggressive than some of the other ones. But what we do here is actually cut that in half down to $32.50 per acre at each harvest. So again, it's a best practice target, but it's definitely achievable. And, this can be done through a variety of different ways. So, one of the things that's developing and, it's done for other crops is soil testing and precise nutrient management. So maybe you don't need to spread nitrogen or a different fertilizer over the entire acreage. If you can identify spots that need it and only do some precision fertilizer, that's one way. Another thing is utilizing organic waste streams that are possibly and usually cheaper than using commercial fertilizers. This has been something that's been studied pretty heavily in Willow, so if any of those types of options are available, you might be able to fertilize and reduce your costs. And then the other thing is simply not fertilizing every rotation if you determine it's not necessary, especially in the first few rotations of the crop production, the first or second or even third rotation. You might have more than adequate fertility existing in your field and really not need to add any. So again, all these things and a combination of these practices, we think it's a realistic goal to reduce your fertilizer costs by half if you employ some of these practices, and at the same time not sacrifice yield. So from there, we'll jump over to the harvest module and do a couple adjustments there as well. So as I mentioned before, this harvest rate can be adjusted in terms of your acres per hour. You have a suggested value. This is based on your standing biomass and the expected performance of this Case New Holland harvesting platform in this quantity of standing biomass, whatever's in the model. So SUNY ESF, Case New Holland, and partners were recently awarded a second grant to continue improving this system and harvesting efficiencies of Willow. So we do expect to see more improvements in the system in the near term and also the long term. So in this improved scenario, we have right now a harvest rate suggested value of 2.8 acres per hour. So again, we're going to make a pretty moderate assumption and just bump this up to 3 acres per hour. And you can see that it changes the tons per hour that's coming out the spout a little bit, about 5 tons per hour more. Again, those variables are basically filtered down through the total harvest time, which is increased now because we increased the acreage, your cost for equipment, etc. And then one other variable that we're going to change and that I'll draw your attention to here under the harvesting module and the equipment heading is this collection wagon or collection vehicle capacity. So the default or the suggested value for this is actually 8 tons capacity for each collection vehicle. We recommend that you use larger collection vehicles, so high dump wagons or some kind of truck that can handle the field conditions, and something that can hold, something more than 8. But for this scenario, we're going to use 12 tons for each vehicle. And this reduces the number of vehicles that you need, so each vehicle can hold more material. So I don't know if you caught it there, but what that did in this scenario actually is reduced your number of collection vehicles from 3 down to 2. And this actually has a somewhat surprising impact on the economics of harvesting. And one of the reasons for that is if you consider that you're harvesting 7 times over the life cycle of the planting in this project analysis. So by just reducing 1 wagon each harvest cycle, you're reducing it by 7 wagons over the entire course of the analysis. So that shaves another $1 or 2 off the total cost per ton of your harvesting costs, again on a wet weight basis. So that's the harvesting module. We jump again over to the input-output module. Those are all the adjustments that we're going to make to the system. So basically, what we did was make 2 or 3 adjustments at each of the different stages of the production system: planting, harvesting, general inputs. So if we look now at the expected net present value, this is now positive, $13,000. Expected internal rate of return is also positive. And the break-even price is actually down to, again, less than $25 per wet ton. So by making small adjustments to just a few variables at each stage of the production based on, mostly modest assumptions of best practices and expected system improvements in the near-term future, we can see that there is actually a potential for profitability for willow crops even without subsidies. And I think it's also, you got to remember too that research for this stuff is ongoing. And now that it's happening on a commercial scale in New York State, commercial producers and business owners will always seek to innovate and improve their own returns on investment. So that is the improved scenario, the third scenario. And now we'll just quickly look at the improved incentivized scenario. So we have the improved scenario all set into the model, and we'll just add back in that $40 per acre per year incentive payment and your $500 an acre one-time establishment. So if you look at the outputs from that, now you have an NPV that's quite positive, internal rate of return over 20%, and a biomass break-even price of less than $20 per ton if you include possible incentives and possible improvements to the system through best practices. And then the last thing I'll show you on this scenario, if we look at the break-even point, it's actually just 7 years after planting for the expected scenario. So that's just 2 harvests after planting. So those are the scenarios, the 4 hypothetical scenarios that we've developed along with EcoWillow 2.0. Again, these are not really set in stone. They're just examples of what may be possible and different variables, how they affect the cost and revenues across the production system. We made a fact sheet detailing all these 4 scenarios. So if you haven't checked that out, you can look on our website and find that, and it will tell you all the variables that I went through just now. And you can play with those and see how they affect the system if you put in different variables. And so I hope you're able to check that out. So to wrap everything up today, I'll just switch back quickly to our presentation. So EcoWillow 2.0, it's pretty widely used and it's freely available for anyone who wants to download it. There's our website again. Please go there and check it out, and also check out the fact sheets and everything else that's there. We've updated the model based on the most current data that we have from commercial plantings, as well as feedback that we've got from producers and other stakeholders. We've tried to make a user-friendly design that's also highly customizable to your own situation. We've created these 4 example production scenarios that show the impact of best practices, incentives, and near-term improvements on the potential for profitability. And those 4 scenarios and the outputs are just summarized down at the bottom. So base case incentivized, improved, and improved incentivized, with your break-even price ranging from $30 to a ton down to less than $20 per ton. Internal rate of return possible, over 20% if you have everything going in your favor, and possibly a payback period, between 7 and 13 years. So thank you very much for your attention today. I appreciate it, and I hope this was informative and useful for you in your understanding of the model and also your use of the model. So from there, if you have questions, and Tim is also here with me, so whatever you have for us, we'd be glad to hear it.
Thank you so much, Justin. To our participants, please type your questions in the chat pod on the left-hand side of the screen, and we'll run right down through them and address all of your questions. I just want to let everyone know that a recording of this webinar will be made available on the New Bio website within a couple of days after this too. So if you want to come back and look more closely at a couple of those scenarios, you can do that. So it seems like, well, there's a question from Anthony. You may have touched on this already, but let's just remind ourselves about some of the input assumptions on amounts of fertilizers, amounts of pesticides. Do you have a resource that we could point our participants to that would highlight those specifically, you know, what the optimized amounts for those types of inputs might be?
Yeah, so I guess at this point, again, on our website, there's a handbook for willow producers that has that information in it. As part of this new bio project, we're process of updating those into a series of fact sheets for different steps in the process. But that producer's handbook is available on the web.
Great, great. Justin, if you wouldn't mind typing a link to that website into the chat pod so people can take a note of it, and we'll also make sure that we publicize it when the recording of the webinar is put up. So it seems like incentivization is really key to profitability in all the scenarios you've highlighted. For people in the greater New York area and other BCAP areas, you know, you mentioned BCAP is a really important incentive program. What others are out there? What should people be taking advantage of? And is this something that people should consider if they're outside of an area like that?
Well, so the only incentives that are currently available that we're aware of were the BCAP, USDA Biomass Crop Assistance Program incentives. So unless there are other sort of state level incentives, there have been in some cases for energy crops. The only federal program that is currently available has to do with the USDA BCAP. So currently there are no new project areas being developed for that, although it is in this round of the Farm Bill. The BCAP program is in there and it has some minimum level of mandatory funding. So we would anticipate that there are going to be opportunities to expand energy crop areas under BCAP in the next few years.
It seems like we have, well, you've had a lot of users who are international users, and I think a lot of people on the webinar today are joining us from outside the U.S. Are those programs more common on a broader scale?
So there's certainly been other incentive programs, particularly in parts of Europe, where they've incentivized energy crops and with the overall overarching policies related to renewable portfolio targets and lowering greenhouse gas emissions. There are some other countries in Europe that have incentives for planting energy crops.
So when you run scenarios for a system like that in Europe, do you find that incentivization is also really what makes the difference between net profit and net debt?
So incentives certainly have an impact. So, you know, the big things are what the big cost factors are: harvesting and transport and establishment costs that Justin showed us in the breakdown graph. And then at the other side, you know, what are your revenues? So the big factor there are yields, right, and the price you're getting for a ton of biomass. So the current price for a ton of biomass here in upstate New York is pretty cheap, and I think most places there are places in Europe where the prices are, you know, considerably higher than the $27.50 a green ton. That's sort of the average here.
Thanks. We have a question about the impact on costs of drying operations. So it's just another piece of the logistics that tends to add a lot of energy and time and labor. Can you speak to that and how it's reflected in the model and projections?
Yep, so it's fairly easy. There's no drying costs built into this model at this point in time. So that's something that could potentially be added down the road. All of the end users that we have worked with and collaborated with up to this point in time have been fine taking material, fresh material or green material that's not dried. So other end users may want to have it dried based on their system or products such as pellets that they want to make out of it. That's not a cost that's currently in here. So I'm just going to go back to it. Anthony asked this question about what is the assumptions for $65 cost per acre for fertilizer, and I don't think I addressed that when I talked about that earlier. So that's for the recommended practice at this point, like in the handbook, is 100 pounds of nitrogen per acre once every 3 years. So after harvest, the spring after each harvest, that's the current recommendation. So we'll also tell you that we've not gotten in the trials we've done much response to nutrient additions. And so whether you actually need that or not, it does depend upon your specific individual situations. So here's an example. So there were about 750 acres or so of newly established willow in northern New York a couple years ago, and Justin went through quite a lengthy procedure. We did soil samples across that acreage for landowners, and then we went through an analysis to try and help them determine if they needed to do fertilizer. Just to give them the acreage. I think there was only one field, maybe 50 acres or something like that, needed fertilization.
Oh, Tim, you're a little quiet. If you could just step a little closer to the mic and repeat that.
So out of the 750 or so acres in northern New York that we worked with landowners and did soil sampling, there was only about 50 acres of that actually, based on the nutrient levels there and what we expect needs to be required for good growth, only about 50 acres needed fertilizing this past spring.
Thanks. Yeah, that's a useful illustration of the need for the user to have as much information about their own operation as possible to get the best estimates out of the model. So it looks like we're winding down on questions. If you have any other questions, please type them in now. In the meantime, I just want to thank Justin and Tim. It looks like we're running up on 2 o'clock now for such a very specific overview of all the inputs, and it's nice to just be walked through a model like this, since if you open it cold, then it's a lot of inputs, it's a lot of stuff to think about, but seeing it in action really helps illustrate how to use it and how it can best be used. So I want to thank you both very much for your contributions. Do you have any final thoughts for us?
Well, thanks again for hosting today, and to everybody out there that's listening, if you have specific questions, we're more than happy to either take your email or take your phone call or however you want to get in touch with us, and we can answer more questions